Matter, dark energy, and the fate of the universe. What is dark matter? Dark matter is a hypothetical type of matter. This existence of this type of matter helps explain puzzling astronomical observations. It is distinct from dark energy and baryonic matter. It makes up 27% of the universe. If scientists can't see dark matter, how do they know it exists? Unlike normal matter, dark matter does not interact with electromagnetic force. This means it does not absorb, reflect, or emit light, making it extremely hard to spot. It is not dark clouds made from baryonic matter. We would be able to detect the baryonic clouds in the atmosphere with the radiation they give off. Supermassive black holes could also be a part of the difference. One idea is that it could contain supersymmetric particles, hypothesized particles that are partners to those already known in the Standard Model. Experiments at the Large Hadron Collider may provide more direct clues about dark matter. Dark matter has important consequences for the evolution of the universe and the structure within. Scientists calculate the mass of large objects in space by studying their motion. Astronomers examining spiral galaxies in the 1950s expected to see material in the center moving faster than on the outer edges. Instead, they found the stars in both locations traveled at the same velocity, indicating the galaxies contained more mass than could be seen. Studies of the gas within elliptical galaxies also indicated a need for more mass than found in visible objects. Clusters of galaxies would fly apart, and the only mass they contained were visible to conventional astronomical measurement. Ordinary dark matter, MACHOs. MACHO stands for Massive Compact Halo Objects. These are dead or failed halo stars of the galaxy. Very dim objects that still have protons and neutrons. Extraordinary matter, WIMPs. WIMP stands for Weakly Interacting Massive Particles, not protons, neutrons, or any form of natural matter. Its particles move too fast, which is what makes them extraordinary. Although dark matter makes up most of the matter of the universe, it only makes up about a quarter of the composition. The universe is dominated by dark energy.
Dark energy. Discovery. Using ground telescopes, researchers began studying supernovas. To their surprise, the supernovae were incredibly dim. They were so dim that the scientists concluded that they were further away than they should be. Their immense distance meant that the universe's expansion is speeding up, not slowing down. Hubble. Researchers turned to the Hubble Space Telescope for a clearer image of the supernovas. Because of its location above the Earth's atmosphere, it is able to observe them in close detail. Hubble proved to the scientists that it couldn't be the atmosphere or dust making the images they received dim, and the supernovas had to be that far away due to the quickly expanding universe. But now their question is, what is causing this expansion? What is behind the mysterious force? They called it dark energy, but it is still a mystery today. Dark energy in our universe. More is unknown than known about dark energy, but according to cosmologists' tested Standard Model, 73% of the content of the universe is dark energy. What is known is that dark energy pushes galaxies apart at an ever-increasing speed. After the universe began, it slowly expanded, and galaxies spread further and further apart. The growing distance between these galaxies also meant the dispersion of the mass in the universe. As the distance between mass grew, gravitational pull started to fade. As the gravitational pull faded, the repulsive force of dark energy took over and began forcing the universe to speed up. Dark energy in our universe. This diagram shows the changes in the universe's rate of expansion since the universe began 15 billion years ago. The shallower the curve, the faster the rate of expansion. The curve changes about 7.5 billion years ago as objects begin flying apart at a faster rate. This acceleration is theorized to be caused by dark energy. Theories of dark energy: 1. The cosmological constant. 2. New field or fluid. And 3. Einstein's theory is wrong. The cosmological constant. A version of Einstein's gravity theory contains the cosmological constant. This theory suggests that empty space can possess its own energy, that dark energy is a property of space itself, and it isn't diluted as space expands. This theory means that more space comes into existence, and as it does, more dark energy, or energy of space, also appears, causing the universe to expand faster and faster. But no one understands why the cosmological constant would be there, and why it would have the exact value to cause the acceleration of the universe. New field or fluid. This theory states that dark energy is a new kind of dynamic energy fluid or field. According to this theory, it is something that fills space, but its effect on the expansion of the universe is the opposite of that of matter and normal energy. Some scientists have named this fluid or field quintessence. But scientists don't know what quintessence is like, what it interacts with, or why it exists, thus continuing the mystery of dark energy. Einstein's theory is wrong. Another possibility is that Einstein's theory of gravitivity is incorrect, which would not only affect the expansion of the universe, but also way that normal matter in galaxies and clusters of galaxies behave. But what other theory would work? Is there another theory that could explain the motion of the bodies in the solar system as Einstein's theory has, while also giving us the different prediction for the universe that we need to explain dark energy?
Have you ever wondered if it is possible for the universe to end and not exist anymore? There are many theories out there about the fate of our universe. These theories are based on the two concepts we have talked about already: dark matter and dark energy. Dark matter is holding the universe together through gravity, but dark energy is working against gravity, trying to expand the universe. Notice in this pie chart that there is much more dark energy in the universe than dark matter. This means that the universe is expanding. It has been calculated that we only have 25% of the dark matter needed to stop this expansion of the universe. So what does this mean for our universe? There are many theories on what the fate of the universe is. The main question to figure out is which theory is the most likely to be true. There are many theories because of how little we know about dark energy. The more astronomers learn, the better idea we can get on the fate of the universe. We will just go over a few of the most likely theories out there. The Big Crunch predicts that the effect of dark energy will diminish, ultimately allowing gravity to win. The universe would stop expanding and begin shrinking. How much it would shrink, or if it would stop shrinking, is the big question. This theory predicts that it would shrink and the universe would become a massive black hole. Opposite of the Big Crunch is the Big Freeze. This theory predicts that the universe will keep expanding and never quit. Stars would fade and die out. The heat would be distributed evenly to where there is not enough to go around everywhere. The result would be a cold, dark state. The Big Rip is kind of like the Big Freeze in that it assumes the universe will keep expanding. The difference is that it assumes the universe's expansion will increase rapidly, resulting in everything being physically torn apart, right down to atoms being torn apart. The last theory we will talk about is the Big Bounce. The Big Bounce is a combination of the Big Freeze and Crunch theories. It thinks that the universe starts in a Big Bang, expands to maximum expansion, and then starts to shrink and form black holes. It shrinks all the way to a point of singularity, then another Big Bang happens, and it starts all over again.